Okay, in the last video, we learned that the majority of this semester is going to be concentrating on how we calculate something called integrals, which is one thing that gives us an area under the curve. As we go further and further into this topic, we'll look a little bit more about conceptually what an integral is or why it's useful, why it's a useful tool to learn. But for right now, let's just assume we want some easy way to calculate an area under a curve. Well, one way to do that is if, for example, if we had this black curve, which I've shown right here, we can break the area under the curve up into a series of geometric shapes. Now, the easiest geometric shape for which it is to apply this is going to be a rectangle. It's easy to calculate the area. It's just base times height. And we can set up any number of rectangles over the span of which we want to calculate the area under the curve. Now, in this particular picture, the orange rectangles represent area above the x-axis, which is positive area, and the purple rectangles represent area below the x-axis, which is negative area. So as you can see right here, if we wanted to approximate the area under this curve, this would be a very easy thing to do. All we would have to do is come up with an algorithm that utilizes calculating the area enclosed by a number which we will call the letter n subintervals, or n rectangles. Okay, so in this particular case, I've drawn these black lines down here just so you can see that these actually do reflect rectangles. But if I come here and erase these, you can see that one way we could make this approximation more accurate is if we added more subintervals. So again, this number n is how many subintervals I have. If I increase it, you see that we get more rectangles, but as we get more rectangles, it looks like our approximation, or the area under that curve, gets more and more and more exactly like what that area would look like. Now, if we make it a very crude approximation, and let's say we only have a couple, like 6, in that case, our approximation is a little bit less accurate. So there's kind of a give and take here. Basically, if you want to have a greater approximation for an area under a curve, you essentially have to use more subintervals. So using these rectangles to create subintervals is a method for calculating an area under a curve known as a Riemann sum, and that's what we're going to be talking about in this video. So there are 3 types of Riemann sums. There are left Riemann sums, right Riemann sums, and midpoint Riemann sums. So this particular Riemann sum we have here is a left Riemann sum. So pause the video real quick and see if you can figure out why this might be called a left Riemann sum. All right, do you have an answer? Well, the reason is because when we calculate the areas of our rectangles, the height of our rectangle, you notice, is always dictated by the leftmost point of which that rectangle hits our particular curve. So whenever we are going to calculate the height of a rectangle in a particular subinterval, we are going to be looking at that leftmost point. Another way to visualize that is that the just the left corner of the rectangle. It could be upper or lower depending on if it's above or below the x-axis. But anyway, that upper left point or that lower left point is always going to be touching our particular function. Okay, so a different type of Riemann sum is called a right Riemann sum. So if we look at that, we'll see that looks very similar, but what happens is we just shift everything over. So now, instead of the left point on the rectangle touching the curve, it is our right point on the rectangle which touches the curve, which is also the point that dictates what height we are going to be using when we calculate the area of our particular rectangle. Okay, so left and right Riemann sums. I'll go over them a little bit more in a couple more slides. But yeah, if that's confusing you, if it's hard to remember, I just flip back, kind of reverse this video a couple times, and you'll be able to see the pattern. Once you recognize that, it's not very hard to tell whether you're dealing with a left or a right Riemann sum. So the final type of Riemann sum that you can do is one called a midpoint Riemann sum. So if in a left Riemann sum, the height of our rectangle was dictated by when the leftmost portion of a rectangle hit the curve, and a right was the opposite, it was dictated by when the rightmost portion of a rectangle hit the curve. A midpoint Riemann sum, the height of the rectangle is going to be dictated where essentially the very midpoint of each rectangle hits the curve. Okay? So based on what type of Riemann sum we're going to be using, that's going to dictate how we calculate the area under our curve, or how we use a Riemann sum to do that. And again, if we have more subintervals, we're going to have a better approximation. Now, in this particular case, we use equally spaced subintervals. That basically just means the base of all of our rectangles are the exact same distance. Now, they don't have to be. They could all be different if you wanted them to. But in most cases, if you're thinking of coming up with an algorithm to calculate these things, it's a lot more effective to have them be the same width. But they don't have to be. So if we come over here and look at our Riemann sums, again, what a Riemann sum is used for is we come up with this number n, which we call subintervals or partitions. We have n rectangles to approximate an area under the curve of f of x, which again represents the area between that particular curve and the x-axis. Remembering that that area, if it exists above the x-axis, is positive. If it's below the x-axis, it's negative.